Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Scaling Laws from the paper Physics at Nanoscale. So the learning objectives of this module are: first, scaling laws, that is time and length scales, and the scaling in mechanics will be discussed. Second, scaling in fluids, heat transfer and biology will be discussed. So students, let us start with a basic introduction about the module. As we go from macro world to the nano world, one comes across two limits. So as discussed previously, when the characteristic dimension of the systems, they are reduced from macroscopic to microscopic domain, the effects of gravitational force becomes negligible as compared to electromagnetic forces. So the adhesion, the frictional effects, surface tension, they dominates over gravity. This implies that our reasoning behind the explanation of the properties at the macroscopic level is no longer valid. However, this argument does not hold in the case of all the properties. So the boundary between the macroscopic and microscopic world is not sharp, and in most cases this boundary depends on the particular effect or the property at macroscopic level under consideration. Now, when the characteristic size decreases further to the nanometer range, another limit comes into the play. So, while the macroscopic properties of matter can be explained at the micro to nano level, but the surface effects become dominant at the nanometer scale. Moreover, in nanometer scale, quantum effects starts dominating over the classical and semi-classical effects. So the scaling laws, they can be defined as the proportionality relations of any parameter associated with the system with its length scale. Now, different scaling laws reveal the fact that the shrinking of the body does not only lead to the size reduction, but it also leads to different physical modifications and properties of the body. So the scaling laws, they are generally deduced at the macroscopic level, and in some cases it may be used to understand the behavior of the microscopic and nanoscopic level. But in many cases, the scaling laws deduced at the macroscopic level, they have to be used carefully due to the fact that several macroscopic experimental conditions are not valid, particularly at nanoscopic level. So in order to explain different properties at nanoscopic level, there is thus a need to modify our understanding and the reasoning. So this results in different scaling laws to understand the origin of the differences between the macro world and nano world. So in the following sections, we will discuss how the properties and effects changes with the dimension of the object and how this is incorporated to estimate the surprising behavior of materials at nanoscale. Basic idea of scaling according to the time scale. So students, for this, no universal time scale exists and it depends upon the process under investigation. So a multi-scale problem in which different processes are scaled with distinct time scales depending upon the phenomenon to be addressed. So this table shows a particular phenomenon and for that a particular time scale. If we have the fluctuation of bonds over time scales, it is around 1 femtosecond. The collisions of small molecules in a liquid separated by, it is around 1 picosecond. Decay of velocity correlations is around 1 picosecond. Macroscopic motion to be observed takes place over time scales and this phenomena is around 40 microseconds. Protein folding, basically short peptides, is around 100 microseconds. Protein folding consisting of the short proteins is around 1 second 2 minutes and lifetime of a cell is around a days or longer. So next type of scaling is according to the length scale. So consider a system with all the 3 dimensions vary proportional to capital L. So here, as shown in the figure, consider a box which is having dimension L, T, that is a length, thickness and height. All are equal to capital L, that is the characteristic length. So hence the surface S and volume V of the object vary as L square and L cube respectively. So let us assume that all the other material properties such as density, modulus, strength, they are constant. Now if we will divide this area by volume, it is inversely proportional to the characteristic dimension length L. So small particles, they have much more surface area compared to the large particles for the same volume. So students, let us now discuss the dispersion, that is surface by volume. This graph shows the percentage of surface atoms on a particle as a function of total number of atoms in a particle. So this percentage is continuously decreasing with the total number of atoms. So this concludes that smaller the particle, larger be the surface area, larger be the reactivity, and the crystal structure depends upon the particle size. Scaling in mechanics. The force of gravity, that is Fg, on an object on the surface of the earth is Fg is equal to mg, which is proportional to m, where g is acceleration due to gravity. So thus Fg is proportional to L cube. So at the microscopic level, the adhesion forces dominates over gravitational forces, and the adhesion force between the two surfaces, either between solid or liquid, and liquid arises due to the forces between the atoms and the molecules. The adhesion is mainly due to van der Waals forces, that is F van der Waals, which varies with the contact area. So this implies that F van der Waals as a function of x is approximately L square. So the ratio between F van der Waals and Fg is approximately L inverse. So hence the adhesion force dominates the gravitational force at nanoscale. Gravity may be neglected at very small scales, that is at micro and nanoscales. The frictional force. The frictional force between two sliding surfaces relative to each other is given by F friction is equal to mu mg, where mu is the coefficient of friction. This implies if mu is constant, then F friction is approximately L to the power of 3. So the frictional force generally does not depend on the contact area. The reasoning behind this law is that the two rough bodies at macroscopic level touch each other only at a very few points, and the actual contact area is much smaller than the geometrical contact area. But this is not the case at the microscopic level due to surface roughness. Now, a scanning probe microscope, like we have AFM, that is atomic force microscopy, can be used to study friction at nanoscopic level by measuring the forces between the probe and the sample as a function of their mutual separation. The tip in AFM is a well-defined, sharp, pointed contact which enables to measure the interaction forces with nanometer resolution. So, it is known for quite some time that the continuum mechanics reasoning breaks down at the nanoscale. At this scale, as it has been emphasized, the macroscopic physical laws are no longer held. For example, the frictional force is no longer proportional to the applied load, whereas it does depends upon the contact area. An understanding of how friction force depends on the applied load and contact area at nanoscale is essential for the design of miniaturized mechanical devices and several other applications. So students, this figure shows a macroscopic contact that appears smooth and continuous, is usually composed of multiple contact points between many microasperities. The friction law for a nanoscopic contact, a single or few asperity contacts, is not known. Scaling in fluids. So students, as we all know that viscosity is a property of a fluid that offers resistance to the flow and arises due to collisions between neighboring particles in a fluid that are moving at different velocities. So, when a fluid is flowing through a tube, the particles which compose the fluid move more faster than the E-tube's axis compared to those particles that move near the wall of the tube. So this results some stress, which is the pressure difference between the two ends of the tube, is needed to overcome the friction between the particle layers to keep the fluid moving. According to continuum mechanics, the stress required for the liquid flow is proportional to the fluid's viscosity. A fluid that has no resistance to shear stress is known as an ideal fluid. Zero viscosity is observed only at a very low temperatures in superfluids. Otherwise, all fluids have positive viscosity and are technically said to be viscous. Generally, a liquid is said to be viscous if its viscosity is substantially greater than that of water. A fluid with a relatively high viscosity, such for example the pitch or the glass, may appear to be solid. Now, the most notable difference between the liquid flow at the macro and the nanoscale dimensions is the high surface area to volume ratio of the fluid channels. Relatively high surface area of liquid leads to effects such as adsorption of molecules onto the nano channel surface and changes in effective viscosity. So as shown in this figure, students, we know that each layer is clearly shown over here and the length of the total system is considered to be the capital L, and the velocity or the viscosity with which they are moving is nu, or we can say V. So these and other interesting nanoscale effects lead to unique phenomena in this regime. The kinematic viscosity V is the ratio of dynamic viscosity eta, which defines the resistance to shearing flow to the density of the fluid rho. So we can say that V is equal to eta by rho. Life at low Reynolds number. Reynolds number is given by the ratio of inertial forces to the viscous forces. So Re is equal to rho mu L UL by eta, which is equal to UL by eta, where L is the typical length scale in the system, U is the maximum velocity of the object relative to the fluid. Now at low Reynolds number, which is less than 1, would imply that the viscous forces dominates. So the Reynolds number encountered by a human will be much larger as compared to a bacterium flowing through the same fluid, because typically L and U are larger. The bacterium encounters a larger degree of viscosity as opposed to its inertial forces. The swimming of bacterium through water is equivalent to the swimming of humans through a thick, gooey fluid like molasses. So the bacterium cannot use the same technique for the swimming as the human, and their move is by churning their way through the fluid with the corkscrew type motion of flagella. Pumping in fluids. The volumetric flow through a cylindrical pipe of radius r, this small r, as shown in this figure, this Q volume is given by, that is through the tube, it is given by pi multiplied by r to the power 4 multiplied by delta P divided by 8 eta L, where r is the radius of the tube, delta P is the pressure drop over the length of the tube, L is the length of the tube. Now, if the characteristic dimension capital L is equal to the radius r, then this Q volume is proportional to L to the power 4. As it is already discussed that the differences in the velocities of the particles of fluid flowing through a tube along the axis of the tube and near the tube surface results a pressure difference between the two ends, and this is needed to overcome the friction between the particle layers to keep the fluid moving. In case of shearing flows, adjacent layers move parallel to each other with different velocities. In nanoscale, where laminar flow of liquid is important. In case laminar flow of fluid or the liquid is known as Coulter flow, a layer of fluid is trapped between the two horizontal plates. One is fixed and one is moving horizontally at a constant speed. In this case, liquid flow is driven by viscous drag and the pressure gradient parallel to the plates. So the liquid which shows Coulter flow has to be homogeneous in the layer and at different shear stresses. So now the next is the volumetric flow, which can also be expressed as the Q volume is equal to, that is U multiplied by pi L square where U is the average velocity of the fluid and pi L square is the cross-sectional area of the pipe. So now the pressure gradient means the pressure drop per unit length, that is delta P by L, is equal to Q volume multiplied by 8 mu divided by pi multiplied by L to the power 4. So this has been done by placing the value of Q volume into the first equation. So now putting the value of Q volume, that is equal to U pi L square multiplied by 8 mu divided by pi L to the power 4. Now pi L square is common in both the numerator and denominator, which leaves us with 8 mu V, or here we are saying at 8 mu U by L square. Therefore, scaling law for pressure gradient scales as L to the power minus 2. Thus, the pressure drop by unit length increases with the decrease in the tube radius, leading to much larger surface to volume ratio of the flow compared to the macroscopic systems. Now, the different techniques of pumping, such as electrohydrodynamic, electroosmotic, and electrophoretic techniques, which depends on the surface of the fluid, have been devised for this scale. Objects falling through a viscous liquid. What takes longer to fall through a fluid, a larger or a smaller object? The force needed to move a sphere of radius R at a velocity v through a viscous medium is given by the Stokes Law, that is F is equal to 6 pi eta RV. Viscous forces on the sphere causes it to eventually fall with a constant terminal velocity. So for laminar flow, Vt is equal to 2gr square multiplied by rho sphere minus rho fluid divided by 9 eta. Now here rho sphere is the density of the sphere, rho fluid is the density of the fluid, V scales as L to the power 2 and viscous force scales as L to the power 3. So the time t that the sphere takes to reach the velocity VL by g, which means that the time scales as L to the power 2. Thus, a larger object will reach the terminal velocity before a smaller one and will fall faster than it. So now let us discuss the melting temperature and the size dependence. So, students, this formula gives us the relation between the melting temperature and the characteristic dimension capital D. That is, T is equal to T bulk multiplied by 1 minus 1 by D. So as shown in these two figures, the melting temperature, how does it vary with particle diameter and surface to volume ratio? Melting point is inversely proportional to the surface to volume ratio. That is, smaller the size, larger is the surface area. Rearrangement of atoms is easier on decreasing the size of the particle. And the melting temperature of particles is always less than the bulk. So students, let us now discuss the scaling in heat transfer. The mechanism of heat transfer is significantly different in small systems. The energy ETH needed to heat a system of characteristic dimension capital L to a given temperature is directly proportional to the system's mass and therefore its volume. So ETH is proportional to M is proportional to V. This means ETH scales as L cube. This relationship holds true for the heat capacity, that is Q capacity of the system, also proportional to mass and to the volume. So it also scales as L cube. Heat can be transferred as conduction, convection, and radiation, but conduction and convection, they are the more common modes of heat transmission in smaller systems. The scaling laws are often valid in two distinct regimes. One is the sub-micrometer scale, which includes systems with L less than equal to 1 micron. The other being systems larger than that with L greater than 1 micron. The rate of heat conduction, that is Q conduct, in a solid is given by Q conduct is equal to minus Kc multiplied by A multiplied by delta T by delta X. So students, as we know that A has the dimensions L square and delta X as L, so L square multiplied by 1 by L is proportional to capital L. This is for L greater than 1 micron. Now, if L is less than equal to 1 micron, then Kc is proportional to L, A is L square, and 1 by delta X gives us 1 by L. So effectively, this Q conduct is proportional to L square. Next parameter is convection, that is heat transferred by the motion of fluid is convection and is governed by Newton's cooling law, which is essentially the rate of heat convection, and is given by Q convect is equal to HT A delta T, and this is proportional to L square for L greater than 1 micron. Here HT is a heat transfer coefficient, A is the cross-sectional surface area of the heat flow, and delta T is the temperature difference between the 2 points in the fluid. Now let us discuss the scaling in biology. Recently, it has been shown that the scaling laws can be applied to living things In general, smaller animals have quicker pulse rates and short lives, while larger animals have slow pulse rates and long lives. So, the life span of an animal varies with its mass, which is proportional to capital L cube. Hence, length scales with mass and length as, or the lifespan is proportional to m to the power 1 by 4. This is proportional to L to the power 3 by 4. Also, the heart rate scales with mass and length as HR is proportional to m to the power minus 1 by 4 is proportional to L to the power minus 3 by 4. So the metabolic rate of animals also scales with its mass. The basal metabolic rate of an animal has to do with its surface to volume ratio. As the size of the living object increases, the less surface area it has to dissipate the heat generated by its mass. So one of the many complex factors that controls the rate of metabolism is that a larger animal's metabolism must be slower than a smaller animal's metabolism to prevent overheating. So metabolic rate scales with the body mass as MR, the metabolic rate, is proportional to m to the power 3 by 4. It is proportional to L to the power 9 by 4. Now, if we consider the mechanical abilities of animals of different sizes, a number of scaling laws emerge. For example, the maximum height or how high the animals can jump. The energy of an animal to jump high is provided by its muscles. The muscular strength can be assumed to be proportional to its cross-sectional area, and hence strength is proportional to L square. The mass of the muscles M proportional to L cube, and thus the ratio of strength to mass is equal to 1 by L. So the ratio is a simplified indicator of how high the mass living object can jump. For example, an elephant does not have sufficient strength to overcome its weight and jump at all, whereas a grasshopper can jump hundreds of times the lengths of its body. So this is a simplified explanation that does not take into account many factors such as shape, orientation, and structure of these animals' muscles and bodies, but does explain quite a bit. Now next is, why do only some birds fly? The animal's ability to fly is curiously follows scaling laws. For an animal to fly, its weight must be balanced by aerodynamic lift alpha, that is, mg should be equal to alpha, and the lift is proportional to the surface area of the wings S and speed of flying v. So alpha is proportional to SV square. Now m is proportional to L cube and S is proportional to L square. Thus, L is proportional to m to the power 1 by 3 and hence S is proportional to m to the power 2 by 3. So, V is proportional to m to the power 1 by 6. So, students, let us summarize what we have learnt in this module. The adhesion forces dominates the gravitational forces at nanoscale. Gravity may be neglected at a very small scale, that is at micro and nanoscales. So, an understanding of how the friction force depends upon the applied load and the contact area at nanoscale is essential for the design of miniaturized mechanical devices and several other applications. Secondly, in nanoscale, where laminar flow of liquid is important, where a layer of fluid is trapped between the two horizontal plates, one is fixed and the other one is moving horizontally at a constant speed. So the liquid which shows the Cauchy law has to be homogeneous in the layer and at different shear stresses. So the heat capacity scales as L to the power 3. Lastly, we discussed that heat can be transferred as conduction, convection and radiation. But conduction and convection, they are the most common modes of heat transmission in the smaller systems. So the rate of heat conduction, that is Q conduction, scales as L to the power 1 and rate of heat convection scales as L to the power 2. Next, we also discussed about the lifespan of an animal, which varies or scales with mass and length as L to the power 3 by 4, and the heart rate HR scales with mass and length as L to the power minus 3 by 4. Thank you.